I want to introduce one of the most fundamental concepts in thermal and statistical physics, the concept of entropy. Entropy, big S, is conventionally defined in terms of our fundamental definitions as K, Boltzmann's constant, 1.381 times 10 to the minus 23rd joules per Kelvin, times the natural log of omega, where omega is the number of microstates in our system in whatever macro state that it's in. So this is a bit of an odd definition, and we'll talk about why we choose this definition in a minute, but I'd like to start out just by doing some calculations, by doing some examples of how it shows up. And just for convenience, I'm going to do these examples in the context of Einstein solids. Now, if you don't know much about Einstein solids, the important thing is only getting to the multiplicity of each one. I'll jump straight to that without doing calculations to get there. So these examples are all taken from things in Schroeder's thermal physics textbook, examples from that book. So we can just work straight from numbers provided there and talk about how entropy shows up there. So in particular, my first example is going to be a very simple, small example where we have an Einstein solid A that has 300 oscillators. I guess that's 100 atoms in a solid lattice, each vibrating in 3 dimensions. 300 oscillators and 60 units of energy above the ground state. 60 total units spread between those 300 oscillators. Solid B will have 200 oscillators and 40 units of energy. And if you do the calculation, you'll find that solid A has a multiplicity, a count of the number of microstates given this macro state, of 1.3 times 10 to the 69th. And solid B has 5.3 times 10 to the 45th microstates available to it. All right, now we happen to know that since A and B are independent systems, they may be interacting, but we're assuming they're independent systems, we can find the total number of microstates in the combined system just by multiplying number of microstates for A times number in B, because you choose one over there, you choose one over there, and you've got that many choices. You multiply to find the total number of choices. When you multiply these numbers, you get 6.9 times 10 to the 114th, which sounds like a big number, though in the context of statistical mechanics, it's practically nothing. But still, it's a pretty big number to deal with. My calculator can't handle it, for example. So, okay, we've got these numbers. How does entropy show up here? Well, I can go through, I can do simple things. Let me just take this omega A and calculate the natural log of omega A. I'll just put that into my calculator. 1.3 times 10 to the 69th natural log. I get 159.14. And if I do the same thing for omega B, the natural log of omega B is 5.3 times 10 to the 45th natural log. I get 105.28. 105.28 as my natural log there. I would do the same thing down here for this total, just to figure that out, the natural log of omega total. But my old calculator actually doesn't do 3-digit exponents. You could work it out by doing some log identities and things. I'm just going to quote it from where I did that calculation earlier, and I found that that gave me a natural log of 264.42. 264.42. That's a 4, really it is. So that's my natural log there. Okay, so these are the natural logs, and remember each one of these is S over K, essentially. It's proportional to the entropy without that factor of K. So if I wanted to work out the entropy for each one, again, I could multiply this by Boltzmann's constant if I wanted to. I'm just going to go ahead, multiply by K. I did this calculation earlier. I get 2.20 times 10 to the minus 21 joules per Kelvin. And this one, I get SB equal to the next one, 1.45 times 10 to the minus 21 joules per Kelvin. And last, for the total, as total for the combined system, I get for that 3.65. Yep. 3.65 times 10 to the minus 21 joules per Kelvin. Okay, so those are my totals. Those are my entropies for those systems. At this point, it's just numbers. It's just definitions. Let me do one more little example, and then we'll come talk about why this was interesting, why we're doing this. The other example, I want to do an example with some realistic numbers. Well, by realistic, it's still an Einstein solid, so it's still an over-idealized special case. But it's realistic in that typical things have about Avogadro's number of particles, and I'm going to choose an Einstein solid with n equals 10 to the 22 particles in it. and the amount of energy in this thing, rather than having all my oscillators be near their ground state, like I did over here for most of the available states, I'm going to choose something where I have an average of 100 units of energy above ground state for each one of these 10 to the 22 oscillators, Q equals 10 to the 24th. For that situation, my omega that I come up with, my number of states, number of microstates for this macro state, is e to the 5.6 times 10 to the 22 power. This number is piddling compared to e to the 10 to the 22nd, which is just laughably huge. So what do we have here then? If this is omega, then I can immediately say, as I did before, that the natural log of omega is equal to, well, 5.6 times 10 to the 22nd, just natural log, that's simple enough. And so the entropy then, the entropy of this system is k times that, 10 to the minus 23rd times 1.3 times 1.381 times this. When I do that, I'm going to come up with an entropy of 0.77, that's a decimal point really, joules per Kelvin. Okay, so why entropy? Now that I've gone through just a couple of sample calculations to show you how this works, why do I care about entropy? Why am I defining this? Let me give you my list. The first reason, write this down. Why this definition? Okay, the first reason is actually the most boring. The first reason is it's historical. History is our friend. This definition of entropy connects it directly back to the foundations of thermal physics and statistical physics back in the day before they even knew how to count microstates, or they should. This connects it back to the history of thermodynamics. Entropy as a quantity was useful and understood pretty well long before we understood about counting microstates. So this definition connects us to that. Second reason, more practical reason, is that if we have a number of microstates that is this e to the 10 to the 22nd business, that is a ludicrously large number. It is ridiculous. No one has intuition for numbers that are like e to the 10 to the 22nd power. It's just too big. It's too big to comprehend. And so by taking the log, the natural log of omega for a realistic sort of omega is usually a more manageable number, like what Schroeder calls a large number instead of very large, which helps a lot. Very large numbers are these crazy things that we just can't even figure out how to deal with. Shouldn't say crazy. Large numbers are at least manageable. So we've got this. And then by multiplying by k times the natural log of omega is then a normal size number. Order 1, basically, or 100, or 10,000, but not 10 to the 22nd. The k natural log of omega, it becomes a familiar size number that we can deal with in ordinary ways. So that's another reason for this definition. The natural log brings our numbers back down to manageable sizes, and k scales it down to be familiar. And then finally, the other reason, the thing that I actually like best, is that omega multiplies when you have independent systems and you want to total up the number of microstates. But with this definition, with this natural log-based definition, any log-based definition, S is additive rather than multiplicative. So when you have two systems and you put them together, you add rather than multiplying. This puts us on an even footing with things like energy, mass, volume, other things like that, other typical what we call extensive quantities in physics. Entropy becomes one of those instead of being the multiplicity, being this multiplicative thing that behaves very differently than the other quantities we have in physics. And this is the one, making S additive is what ties it into the historical definitions and what makes it work for those older ways of calculating these things. That's a glimpse of why entropy works this way, and we can check it, right? Let's look at this in my interacting system, where I had to multiply 1.3 times 5.3 to get 6.9, and multiply those 10 to the things to get this 10 to the 1/14th. Here, for entropy, 2.20 plus 1.45 is 3.65. Hey, 3.65 10 to the minus 21, or without the k's for this one, since it's not a macroscopic size system, these numbers add up nicely too. Taking the log makes it additive. This adds up very nicely. We can just add entropies. There's some subtleties there for things like identical particles and other sort of mixing effects. We can talk about those in other places, but for right now, just getting the concept of entropy down, this is the story. We use this definition, we use these things, and we get a pretty solid use, a pretty solidly useful quantity, S, the entropy of the system, that we're going to be able to use in lots of other places. That's where the definition comes from, and I hope it makes some sense.